My name is Qiao Xiang. Today I'm happily presenting on behalf of Tony Wang, Shenshen Chen, Andy Wally, and Richard Yang for their work on Magellan automatic SDN pipelining from algorithm policies. So in this talk, we'll talk about I'll talk about our algorithmic SDN programming model, and then with a brief introduction about our previous Maple runtime system and its limitations. Then I will give the overview of our Magellan automatic SDN pipelining system and summarize our work. Our ultimate goal for algorithm SDN algorithm SDN programming is that we want the programmers to write the most obvious SDN code. That being said, we envision a programming model that the programmer considers every packet as an incoming request. And the programmer will write the network control functions that returns how a packet traverses the network without need to figure out how data path should be configured. And this network control function should be expressed in general purpose language so that people do not need to learn a new language. And this function will logically be invoked on every incoming packet. Here is an example of a very short AP written in Java. And when a packet enters the network, and if its TCP destination port is 22, we simply drop it. Otherwise, we get it MAC source and MAC destination address and compute the routing path using predefined routing algorithms. And in this short snippet of code, the programmer does not need to specify anything on flow tables. So in this way, the programmer's life is much simpler. Just give a packet, we'll handle it, and the programmer does not need to worry about the low-level details. Well, even though this AP programming model is very simple, implementing it to simplify programmer's life is not a very easy job, because a naive solution of process every packet back at its controller is simply impossible. Then the key challenge is that given a data path oblivious our algorithm policies, how can we use the data path, or how can we generate the flow tables? And in our previous work, we designed Maple dynamic tracing runtime systems, which can trace the execution of the invocation of each algorithm policy F and transmit the execution trace into the corresponding flow tables. The basic idea is that, like I said, the basic idea is even though the decision of the function f, or say APF, does not specify how flow tables are configured, if we are given a decision and we can know the dependency of this decision by tracking the execution of this execution process of this packet, and then we can transfer this decision dependency into the corresponding flow tables. And to use Maple, the Maple runtime system, the only requirement is that when the programmer writes the APs, we use a simple library to access packet attributes. And it's not just for convenience, but it also enables the Maple to track the decision dependency. And the general overflow for Maple is that when a packet enters the network, it will be processed by the controller by executing the function f. And during the execution process, Maple will observe the decision dependency of f on different packet attributes. And based on the different value of the packet attributes, and we build a trace for this packet. And for every packet entering the network, we build a trace, and we convert all these trees into a trace tree, which is a universal decision tree for the function f. And in the end, Maple will compile the trace tree into a flow tables and then sends the flow tables and with corresponding entries sent to the data plane. We use these examples to illustrate our tracing methods. Suppose this is still the same code shown for the example AP shown in the previous slides. Suppose a packet with source MAC 1, destination MAC 2, and TCP destination 80 enters the network. So we will first check the assertion whether the TCP destination is 22. Because in this case, 80 is not 22, so we'll go to the false branch, and to get the source MAC and destination MAC. And eventually using these two pairs and using this pair to compute the corresponding path. And this is the trace for this packet when executing this routing function f. And using these trees, we can build a tree. We then build the trace tree dynamically. This trace tree is basically because currently we do not know what will happen when the assertion of TCP destination equals 22 will hold. We simply just put a placeholder on the true branch, and you construct the trace tree. And say if later we have another packet with Ethernet source 1 and that TCP destination 22 comes in the network, and we'll execute F on this packet again. And in this time we found assertion to be true, and the decision is to just drop this packet. We'll just merge these trees into the existing trace tree and update the corresponding entries, corresponding leaf. So having built the trace tree, transform the trace tree into flow table entries is actually quite simple. We just notice that for each pass from the root to a leaf in the trace tree, it can generate a corresponding matching rules. For example, if there's a packet that TCP destination is not 22 and the Ethernet destination is 4 and source destination Ethernet source is 6, and it simply be forwarded to the port 30, and we have this we can generate this flow rule here, and for each pass, for each leaf, we can generate one rule. But notice that because in current flow rules, we still have this condition of TCP destination doesn't equal to 22. This is a negate match, and is not allowed in the switch. So to eliminate that, we simply insert a barrier rule that we remove these conditions and simply insert another rule that match this condition to be held, but with a higher priority, which we call this a barrier rule. And we simply, this is basically a dumb rule to prevent the flow rule generated on the false branch to be executed when TCP destination equals 22. And when we generate the flow during the process, we generate the flow rules. We simply assign the priorities from the false, starting from the false branch of the trace tree, and then with a higher priority to the barrier rules, and with the highest priority to the true branch. So in these examples, for the two flow rules on the false branch, we can generate a flow priority 1, and for the barrier rule, the priority could be 2, and for the true branch, the flow rule priority will be 3. So using a simple, very classic in-order tree starting from the false branch of the trace tree, we can generate flow rule tables, flow rule table, and very efficiently. And Maple greatly simplifies the programming of SDN, simplifies control plane SDN programming, but it has its own constraints. The first one is that currently Maple only can compile flow rules into a single flow table. And this would because in a packet we have multiple packet attributes, and the packet attributes, the cross product between packet attributes will make the single flow table has a huge size. And the second one is because Maple essentially takes a reactive approach that waits for the packets coming to the packets, pointed to the controller, and then to trace its trace and generate the flow rules. And the latency could be high. And we use this simple GVP example to illustrate the importance of multi-table. Why we want a multi-table pipeline in SDN in switches? This is a very simple GVP examples. When a packet comes in, and we get the conditions based on its source MAC and destination MAC. And if the condition two conditions pass certain tests, we forward this packet using port 1. Otherwise, we just drop this packet. And when we assume there are n hosts in the host tables, and the trace tree after we ping among all n hosts will be a huge complete tree with n square leaves. And with n square leaves, and this we will correspondingly have n square flow table entries. And if we are under attack, there are more packets with whatever arbitrary host name comes in, the flow table size will be even larger. However, if using a using two tables can very easily reduce the size of the flow table. Assume we have k conditions in the hash map of the MAC condition hash map, and we can use a register in the first table to match the source MAC and the corresponding condition. And then in table 2, we only need to do a cross product match between the register and the destination MAC and take for corresponding actions. So in this way, this two-table design only have n plus kn entries. And even a more efficient design would be a three-table design. This is actually optimal in this example. And in this example, not only for table 1, but for table 2, we use another register to match to record the destination MAC and the corresponding conditions with k different possible values. So in the third table, we only need to cross product between the value of two different registers, which is k by k entries. So in this one, in this design, we only have 2n plus k square entries. And a simple comparison between these three designs assume we have 4,000 hosts and 100 conditions. With one table, we will have over 16 million. We have 60 million flow rules, but with two tables, we reduce it down to over 400,000 rules. But with three tables, only have 18,000 rules. So with this example, we see that the multi-table can greatly reduce the size of flow tables, and hence can speed up the data plane processing. So motivated by these examples, in this work, we propose a Magellan, which automatically design the multi-table layout and populate the flow entries given an algorithm policy. And compared with Maple, we see that Maple is usually a black box approach. It's reactive to packets entering the network. But Magellan takes another extreme approach, a white box approach. It basically proactively explores the whole program and generates the flow table entries. The basic idea of Magellan is that given a function or APF, it essentially consists of a sequence of instructions, I1 through IN. And for each instruction, we may insert it as a table because basically it's a table mapping from the input variable states to the output variable states. So using the GPP examples, we see that essentially there are the first three instructions can simply be used to construct three different tables. It naturally leads to the optimal three-table design. But using this per instruction table algorithm does not solve all the problems because it risks two new problems. Because the first one is the table size even though we have multiple tables, the table size can still be very large. Because for each instructions, we still have to take care of the cross product between different input variables. The second problem is that compared with the number of flow tables allowed in a switch, the number of instructions in a program is usually just much more. So to solve the first problem, to reduce the table size, we basically try to, our basic idea is to identify what we call the compact-mappable instructions in a given program. And still using the GPP code for examples, we see that the first instruction I1 to the hash map table lookup, the host table lookup is actually a CM instruction. And in this one, the table construction does not need to consider all available state information of the source MAC. It simply only needs to use all n values in the current host table state to generate the table, to populate the table entries. So in this way, the table size should be n plus 1 instead of 2 to the power of 48. So in this way, we greatly reduce the size of this one table. And not only this kind of table lookup instructions we call it CM compact-mappable instructions. There are also other kinds of mappable instructions. For example, the comparison between two different packet attributes and the comparison between the packet attributes and another variable. All such of instructions are compact-mappable. So using these compact-mappable instructions, we can efficiently reduce the size of each instruction table. And even better, this compact mappable effects can propagate to a next table through data flow. For example, the initial CM we identified is in I1, and similarly we have this I2. But when we constructed the flow table when we construct the flow table and the corresponding entries in I1 and I2, we see that only the output in I1 and I2 tables are needed as the inputs to I3, which is the all k possibilities all k possibilities in the hash map. So using this, by identifying compact mappable instructions, we can successfully reduce the size of each flow table. And to solve the second problem, we basically we essentially need the table design algorithm with a bounded number of tables constraint. And the problem formulation is the problem definition is that given a flow table deadline with at most m tables, and input function, can we compute the minimal size of new pipeline with the number of tables bounded by m? The key issue is that the basic idea is that of Magellan is every instruction can be seen in a table. So now we want to aggregate them into fewer tables. But if we want to just combine any two tables, if say one table is matching on attribute 1, the other one is matching on attribute 2, it can lead to the combination explosion, the cross product again. So that makes all our efforts just waste for nothing. So a naive algorithm would be to consider this table design problem as a graph partition problem with a number of partitions bounded by m. And we can simply enumerate all potential partitions. But suppose we have at most m tables and n instructions, there are a total of m to the power of n possibilities. It's just simply not possible. It's very time consuming. So alternatively, we designed an efficient enumeration algorithm to get the partition. The insight is that usually for written algorithm policies, we usually use a small number of packet attributes. And for a given set of packet attributes, for all instructions that is determined by these packet attributes, for all instructions use this set of packet attributes as an input, we can just simply merge them into the same table. And using this very simple example, we see two instructions, I1 and I2. Both instructions use the source MAC as the input. So in this way, we can merge these two instructions into one single table, so that we do not need two tables instead. So due to time, I omitted the evaluation result. So, to summarize, we basically we aim to design an algorithm policy programming model in which programmers do not need to care about how to configure the data paths, but they only need to focus on designing algorithm and to design the network control algorithms. And the key challenge in supporting this programming model is to get the data paths from data path oblivious programming policies. And in our previous work, we use Maple, a reactive approach that dynamically traces execution of all incoming packets to generate flow rules into a single table. But realizing the latency and the quality of the Maple of the generated table by Maple, we designed an alternative Magellan, a white box approach, which automatically derive and populate tables into multi-table pipelines. And in a typical L2 learning and routing applications, we end up with 46 to 68 times fewer rules than Maple and other popular controllers. So by now, I think I'm a few minutes over, but I'm happy to take questions. Thanks.